Hi everyone, we are very excited to share our research, Mahalanobis distance-based multi-view optimal transport for multi-view crowd localization at ECCV 2024. Multi-view crowd localization has been proposed to predict the people's locations on the ground of the scene. Current methods mainly rely on fixed-size Gaussian kernel density maps as supervision to train models. However, these methods' localization performance is limited by the ambiguity of the density maps in crowded areas, where there may not be clear density peaks over each person for localization. To mitigate the problems of Gaussian density map supervision in localization task, we propose to use point supervision directly. Optimal transport loss directly uses point annotations as supervision and generates more compact density maps, which has been studied in single-camera crowd localization. In this paper, we explore using OT loss for multi-view crowd localization. We follow the loss formulation in previous single-view crowd localization task, which is based on an unbalanced optimal transport formulation with Euclidean distance cost. A is the density of all pixels in predicted density map. B is the ground truth dot map. P is the transport plan matrix, which assigns each density value in predicted density map to ground truth dot location. C is the transport cost matrix. Each value in C measures the cost of moving the predicted density to ground truth dot location. The second term is the entropic regularization term. The last two terms ensure that all predicted density values have a corresponding annotation and all ground truth points are used in the transport plan. We propose 4 types of cost matrix C on the ground plane for each single camera. The Euclidean distance in the transport cost matrix C, denoted as EOT, is the most basic one, considering all directions of deviation from the ground truth point equally. However, the projection step, which projects features from the camera view to the ground plane, introduces streaking artifacts in the feature map. To counteract this effect, we use Mahalanobis distance to replace the Euclidean distance, where the contours of the Mahalanobis distance are guided by the view ray direction, denoted as MVOT. In this way, the predictions that deviate from the ground truth along the view ray from the ground truth points are assigned with larger penalties. We first calculate the covariance matrix for each GT point. Sigma is the variance matrix with diagonal entries squared sigma 1 and squared sigma 2, corresponding to the variances along the view ray direction and perpendicular to the view ray direction. Here we set squared sigma 1 smaller than squared sigma 2, indicating deviating predictions along the view ray direction incur larger loss value. Besides, the object-to-camera distance could also adjust the calculation of the cost matrix for different regions, where faraway points tend to have larger prediction errors, denoted as EDOT. DCAM denotes the distance from the ground truth point to the camera. When DCAM is larger, squared sigma 1 and squared sigma 2 decrease, and thus more penalties are assigned. To consider both the influence of the view ray direction and object-to-camera distance, we use the object-to-camera distance to adjust the long axis and short axis extents of the ellipse isocontours in the Mahalanobis distance, denoted as MOT. Specifically, for the GT points that are far away from the camera, a larger variance is assigned perpendicular to the view ray, which results in a smaller penalty for deviations perpendicular to the view ray and a greater penalty for deviations along the view ray. We further introduce the Mahalanobis distance multi-view optimal transport by combining the proposed Mahalanobis distance optimal transport via a distance-based selection strategy. Following this strategy, we extend our EOT, MVOT, EDOT, and MOT to multi-camera view settings for multi-view crowd localization tasks, denoted as EMVOT, MVMVOT, EDMVOT, and MMVOT, respectively, where the closest camera is used to compute the cost function for a given ground truth point. The overall model architecture is presented below. We first extract camera view features through an image encoder, then project camera view features onto ground plane via camera intrinsic and extrinsic parameters. The projected word plane features are fed into an word plane decoder to predict the crowd occupancy map. The whole architecture is trained through the proposed MMVOT loss. Each point's transport cost C is calculated via the Mahalanobis distance under the closest camera. We conducted experiments on 3 datasets. CVCS is a synthetic multi-view crowd dataset containing 31 scenes, where 23 are for training and the remaining 8 for testing. Each scene contains 100 multi-view frames with about 60 to 120 camera views. Wild Track is a real-world single-scene multi-view dataset. The dataset consists of 7 camera views and 400 frames. 360 frames are used for training and the 40 frames for testing. Multiview X is a synthetic single-scene multiview dataset, also including 400 multiview frames, and the first 360 are used for training and 40 are for testing. We compare the proposed MMVOT with other multiview crowd localization methods on CVCS, Multiview X, and Wild Track. The proposed MMVOT loss achieves better overall localization performance than existing multiview crowd localization methods. These results validate the advantages of our proposed MMVOT loss. We show the visualization result on the three datasets. Generally, the proposed MMVOT, EMVOT, shows better localization performance under crowded region and reduces the projection artifacts of comparison methods on faraway regions. We compare the visualization result of MVMVOT, EDMVOT, and MMVOT. The blue triangle is the camera location. MMVOT predicts fewer artifacts than MVMVOT and EDMVOT, demonstrating the effectiveness of MMVOT. We conducted an ablation study on the setting of the MVOT loss on the CVCS dataset, comparing the proposed MMVOT loss with MSC, EMVOT, MVMVOT, and EDMVOT. MMVOT achieves better performance than other losses, which demonstrates the advantage of the proposed distance guidance and view ray direction in the covariance matrix over other losses. We also conducted an ablation study on the alpha and tau of MMVOT on the Multiview X dataset. Alpha adjusts the object-to-camera distance in the MMVOT loss, and tau adjusts the effect of the last two regularization terms. The best result is achieved at alpha equals to 0.05 and tau equals to 20. In this work, we propose a novel MMVOT loss, which is specially designed for multiview crowd localization. As far as we know, this is the first study on point supervision for multiview crowd localization methods, which advances the research on multiview crowd localization tasks. The proposed loss uses view ray-directed and object-to-camera distance-adjusted Mahalanobis distance in the cost calculation in order to counteract the distortions created during the projection step, and then it is applied to multi-camera views by calculating the cost under the closest camera. The experiments validate that the proposed MMVOT loss achieves better localization performance than density map-based MSE and Euclidean distance-based losses.